So, can you hear me fine? Okay. So, thank you for coming to everybody. My name is Manu Sánchez. I'm a software engineer in a company named By Design. We are specialized in access control systems, like the usual stuff you use to check in at your company, access your bank, stuff like that. Since 2016, I think I'm a member of the Spanish C++ national body of ISO. And yeah, completely self-taught in C++. I never get a course or anything, but I'm here. I don't know if that is a good thing or not. So, unit testing. What is unit testing? If you get whatever book you like, there are tons of books about unit testing and design. Unit testing consists in running black box tests. Like you know nothing about the internal implementation, you only put some inputs in the class or your object or your module of your library, and read the outputs and check if everything is working fine. Okay, ideally, you have to have no dependencies in the unit test, so you can check every input against every output. Okay, there are no implicit inputs in the module or API or whatever you are trying to test. And finally, ideally, you try to test only one functionality at a time. Okay, but in the real world, you usually are working with a legacy code base where for the first 4 years, nobody brought a unit test, nobody thought about testing or checking or whatever. Everything was pushed directly to production, so you have a mess, a complete mess to follow the guidelines that say unit testing is this, and it's done that way. So also, even if you are trying to write a good system from scratch, software systems are complex, are really hard to get right, are really hard to design in a way that they are composable, they are testable. It's really hard. So even if you're starting from scratch, you usually end up with a mess. And in the real world, only cool kids start projects from scratch. So what can we do? What are the usual solutions for these problems? Again, if you take a book, they'll talk about mocking, fakes, spies, stubs, whatever, okay? Everything can be summarized in dependency injection. What it means? It means that if you take a classical implementation of a module, in the example, a file downloader, that takes a URL to a server to download files, and it resolves the path to a file. You take a path, you take a file name, and it magically resolves the URL for you and downloads the file. The problem with this approach is that this class has to know how to initialize itself and all its dependencies. In this case, it has an embedded repository, a full and real file repository connected to a server, and every instance of this file downloader has a full-fledged repository instance. So if you instance this class, this file downloader, and try to download a file, even in a unit test, you're actually connecting to a server and downloading a file. So this is not black box anymore. This is not zero dependencies anymore. This is not a unit test. Okay, this is cheating, actually. You should have a fake server or whatever in your infrastructure to only test this downloader. So the usual approach to solve this is dependency injection, which means instead of having the class instance every dependency you inject or pass as parameter, every dependency of the class or the instance of the class to the class itself. So you no longer have a full instance of the file repository, but you have a reference to an abstract API of file repositories. So you can have a reference to a real file repository, usually in production, or you could have a fake file repository just for the tests. Something like this. You can inherit from the interface of the file repository and write a fake file repository that does nothing. And run the test like this. Okay, you are no longer downloading everything, you're running everything completely fake, but the test works and it's a unit test. What's the problem with this approach? The usual approach of passing references to the object through the constructor doesn't work well for real cases. Works well for tiny example cases like this, but once you start having a large architecture with thousands, tens, whatever, of modules, recursive dependencies, inner layers in your application, passing every dependency through every layer of your software, it's really, really complicated, almost impossible. The other usual solution is using dependency injection frameworks. Okay, the usual stuff that you register your interfaces in a system that once you require an instance of that interface, the system automatically constructs it for you, either be it fake, either be real, depends on how you initialize the system, the dependency injection framework. The problem with this approach is that these are basically singletons. Okay, these are singletons of factories. So if you write a complex system, a complex application, library, whatever, framework, with a dependency injection framework, you end up having really, really hard problems to track what is the lifetime of the different modules of your application. Okay, I don't want to have to debug step by step my application, the startup of my application, only to understand how it is constructed. Okay, I don't want to run a profiler with a timeline just to see, okay, the file manager is initializer first, then the logger, then the downloader. No, I just want to read the code and understand what is going on. So no, factories are not either a solution. But for me, the real problem of dependency injection is that it forces you to change the design of your software to adapt it to testing. Okay, you no longer have a class with a well-defined API, with a well-defined constructor that takes its parameters. No, you have a bunch of reference parameters or pointers or whatever that are there just only for testing. I don't want to change my code only for testing. Okay, so I'm not saying dependency injection it's bad. Okay, I'm saying it's bad only if you apply it for testing. There are use cases where dependency injection works really great. Okay, and this is the usual example I give always. Say your company has an application that has to communicate with various remote systems, say devices like IoT or servers or whatever, okay? So your application, at the level of the business operation, has a well-defined application protocol with commands, statuses, whatever, okay? And you have a class like this that represents the communication stack of your application, okay? And you have, this is overly simplified, but it works as an example. You have a send method of your communication stack that takes a command. Command is the representation of whatever command in your application domain and returns a response in your application domain. Okay? And it internally does serialization of the command into a beta array it does deserialization of a byte array that supposedly really represents a response and returns the response. And then you have a connection to a socket that does the real communication through whatever TCP in this example, okay? The problem is, in this design, you have tightly coupled the implementation of the application protocol and the actual communication of this protocol, okay, the communication channel. So if you try to say, okay, your CTO or your boss comes one day and say, okay, we have to change the protocol and stop using TCP and use WebSockets or whatever, you have to change the actual implementation of the communication protocol of the application. Okay, these are not pluggable in any way. So you can change it to use a dependency injection way, an inversion of control way. That is, instead of having a hard code implementation of the socket connection and a hard code implementation of the serialization and deserialization of the application protocol, you have a generic marshaller that does the serialization stuff for you, and you have a generic connection that does the connection for you, okay? And all your communication stack at the application level works on top of just two modules, completely abstract. So you can have something like this. You can have the legacy implementation of the protocol that somebody brought like 20 years ago in C, following whatever HTTP protocol. You could have a protocol buffers 2 protocol because you decided in the version 2 of the application you will want to use protocol buffers to stop reinventing the wheel. You could have a protocol buffers 3 application, or you could have a JSON protocol, whatever. And at the same time, you could have a serial port communication socket, a TCP socket, a web socket, whatever, okay? And you can combine those two modules, the marshaller and the connection, to implement every combination of deployment you could have in your devices. You could have a device that works with a TCP connection, but the payload is sent as JSON. You could have a WebSocket that uses protocol buffers 2, whatever, okay? But the communication stack, the implementation of the communication stack is exactly the same, okay? Nothing changes. So dependency injection has its use cases. I'm talking only about dependency injection for testing, okay? So what if we can have everything good about unit testing, about mocking, about dependency injection, without the problems of dependency injection? Without the big problem of dependency injection, that is changing your code to adapt it to dependency injection, testing, and mocking, okay? And also try to focus on tests when you write unit test. Try to write as less code as possible to write a test. No setup code, no main file with setup code of the unit testing framework, nothing. Just a function that runs a test, that checks some preconditions, some post conditions, and it returns a diagnostic, okay? We could try mimicking what Python does. Python has an awesome unit test package. It's a standard package of Python that implements test cases, asserts, check-ins, every combination of checking you will need. Also implements mocking. Everything is there in the unit test package, okay? So you can have something like this, an example class. For those of you that don't know Python, self is like the implicit this of C++, okay? So you have a class with a method identity that takes a value and returns a value, okay? That's nothing, the function. And a method that calls identity and only calls identity with 42 as parameter, okay? So you can have a unit test like this, okay? I want to write a unit test that checks that when I am calling the method that calls identity, it's actually calling identity with the argument we expect, okay? But if you check the class again, here there is no virtual function, there is no injection, there is no whatever, okay? But I'm actually checking the actual calls. I'm installing a mock to check the calls to the identity function. The trick is the unit test mock patch function, okay? Mock patch is a function decorator for Python that what it does is to check the thing that Python is completely runtime typed, okay? It's dynamically typed. It has all the type information at runtime. So they can do something like, okay, if somebody instances the class foo in this scope, instead of returning an instance of foo, we will return a mock class. Okay, this is what mock patch does. Okay, it patches, so substitutes the implementation of a method, a class, an attribute, a member variable in C++, or whatever else, and returns the mock you need to actually test the function. Okay, so for example, in the first call mock test function, you are actually mocking the method function. So once you instantiate a my class, you call method, you're actually calling the mock method. You are not calling the original or real method, okay? And you can check, okay, method was called one time with these arguments, etc. Okay? And if you don't install a patch, the mock method, the method, it's the real method, and everything works as expected. Okay? And this is the usual output of a Python unit test. Okay, if you, I think it's, yeah, it looks fine. If you look closely to the command line, I'm not passing any path, any argument, any name of test. I'm not passing nothing. I'm just calling the unit test module in this current directory. It automatically scans for any Python module in that directory and runs any test that it can find. Shows the results and shows you a summary of the results. Okay? For example, when a test fails, it shows you a backtrace, the name of the test, the expected arguments, whatever. Okay? So if you want this kind of stuff in C++, you better switch to Python and have a nice day, okay? Because this is C++. We all know that C++ is horrible and ugly, okay? It's true. So maybe not. Okay, maybe we can have nice things like the cool kids do in Python or JavaScript or whatever in C++. Okay, we can have something like this. An example test case with a patch that patches our identity function, and our identity function is not a virtual function, it's not mocked in any way, it's not injected in any way, it's just a normal C++ class function. And if you run this, you get something like that output. And if you look closely, it actually looks better than the Python backtrace. Okay? You expected a call to identity with 42, but identity was called with 43. Okay? This is real C++. This is not just a slide, okay? So we can have a nice interface to write tests. We can have non-intrusive mocking of C++ methods. We can have transparent test discovery. We can have all the nice things in C++. How? Let's go step by step, okay? First, let's look at how to implement non-intrusive mocking of C++ methods in this case, okay? To simplify the talk. We can also mock free functions or whatever, but let's stick only to C++ class methods. There are different approaches. You can do direct monkey patching of executable code at runtime. Okay, you can get your executable, patch the code, remap it to the virtual memory space, and rerun it. Okay, this is cool, but hard. I don't recommend it. Okay, well, if you do it for fun, it's fine. Okay. You can also patch the lookup table of a dynamic library. Okay. Dynamic libraries usually have a full table of all the functions this library exports and the pointers to them. So you can patch this table and change the pointer and point to your own function. And you have to remember to get everything back right once you stop running your test, okay? Because else you are messing everything bad. And you can also patch directly the virtual function pointer of your class. This is, for example, what HippoMox does, okay? I'm using elfspy because the interface it gives, it matches perfectly for my use case. With HippoMox, it could be working exactly the same. So elfspy. Elfspy, what it does is to, as I said, to patch the function table of a dynamic library. Okay, the dynamic library being the API or library you want to test. Okay, you have to make sure that it's built with debugging information, it's built with, as a dynamic library, it's built with LTO, everything, okay? But it gives you a nice template, a nice class to actually implement a hook into the table. Okay, you give it the signature of your method, the actual class of your method, the name of your method, and then the pointer to the method you want to patch. So it internally lookups through the table, finds your pointer, patches it with its own implementation through a trampoline, and does whatever it does under the hood to give you a mock. Okay? And it gives you, this hook class gives you a nice mock-like interface to check calls, checks the number of calls, the different arguments of the different calls to the function, etc. Okay? So this is a simple example of using elfspy directly. You have a class, and as you can see, this class and this method is not virtual in any way. Okay, this is just a class with a method. You could implement a method hook for this specific signature of function. A method that returns void is a member of the class and takes an int as parameter. Okay, and you construct it with the function name and the function pointer. And then you can do something like this. You instance an object of class, and then you instance a hook of the method of class, and you run your method. And the hook internally registers any call to this method. And you can check the function arguments, you can check the number of calls, etc. And once the hook goes out of scope, the hook is uninstalled and everything goes back to normal. Okay, so the second call in this example to method is just a normal direct call to method. Okay. So the second problem, automatic test discovery. Before going into detail on how to automatically discover tests, let's define some rules. Okay. In this example, I will say that a test is any method or public member function in C++ Linga that its name test underscore blah, 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 okay? And member of a test case class. And the test case class is simply a class that inherits from test case, whatever. So the algorithm or recipe to find a test function is as simple as check every class declared by your unit test executable in this example, and check if these classes inherits from test case. For every potential test case class you find, recurse through every member function checking the names to see if these are named test underscore whatever. Okay, and for every member function or method found, you instance a test case instance and run the method. Okay, so how do you do this? Using reflection. Okay, static reflection in this case. You could use dynamic reflection, but the cool thing about static reflection is that everything is done at compile time, so everything is type checked. Okay, you have no weird runtime error saying, okay, I expected a call with a string and you give me an int or something like that. Okay, everything is checked at compile time, so everything is safer. So I use my library tinyrefl. Tinyrefl implements both a concept-per static reflection API and both a parsing at code generation tool, because as you know, C++ has no reflection yet. And it implements also built-in CMake integration, so you don't go nuts using the library and integrating the code generation tool into your project. Okay, it has a nice CMake function with a nice CMake module that you can find and directly call, okay, this is my library, I need reflection for these headers. Okay, you only call the module, you define your library, and you tell tinyrefl to run the tool for my library and my headers. Okay, everything else is done under the hood. The generated code. The generated code is completely independent from the API, okay, from the Reflection API. You can write your own API, you can use the default or built-in API, everything works, okay. The metadata is represented as macros, as C++ macros or C macros or whatever, because re-implementing an API is as simple as finding a representation of each entity of the metadata. Okay, you can define what is a class, what is a member function, what is an enumeration, what is an enumeration value, how a class is registered into your system, whatever. Everything is declared as a simple macro that you can redefine and do whatever you want, okay? The generated code includes version checking of the generated tool that generated the code, the generated code, the API, so everything matches and you have no surprises, okay? The metadata includes full entity information of C++ with the usual entities we work, namespaces, free functions, overloaded free functions, static member function, classes, and whatever you want, okay? Multiple metadata files can be included sequentially in the translation unit and everything is merged together. So you have two files using namespace A. You will find in the reflection metadata a namespace A with the contents of both files, okay? It's not completely file point of view, the reflection metadata, okay? And also you have a full list of all the reflection entities that are registered into the metadata, okay? So you can do a simply for each, every declaration of your library, check whatever, okay? The implementation of the library includes the metadata representation and also a default implementation of an API. This API is fully concept-per, okay? And implements an object-oriented interface. Okay, this is an example of your library, of your API of Reflection. You have a class object representing classes that takes the name, a method, whatever. Okay, it's just an example. But usually you end up using the default API. The default API represents each C++ entity, say a namespace, say an enumeration, say whatever, as a different context per class. Okay, you have a class representing enumeration, you have a class representing classes, you have a class representing an actual header file with all its contents. Okay, and every class, among common stuff or for every entities like the file, the full name, or the children and the parent of the entity, each class has its own unique API to access the unique properties of each entity. For example, the enumeration class has an API to access members by name, by the underlying number, by whatever, okay? An API that has no sense to have in the class, okay? And also you have a single access point to reflection metadata through the metadata template, okay? This metadata template you can call either through a type. For example, in the example, you are asking for the metadata of the class, and you get a context per instance of this class metadata, and you can static insert whatever. For in this example, that the full name of the class is namespace mylib : class. Okay. The API also implements a visitor API to ease with the transversing of the metadata, generic introspection, finding stuff, whatever. Okay, and the visitor API works by walking through any entity registered and named in any way you could want, either by a type, either by its full name, like in the example, you're trying to visit all the entities declared in the file mylib.hpp, okay, and also has different, let's call them filters, to only visit the kind of entities you are interested in this example, classes. Okay, so in this example, what it is doing is traversing all the classes declared in the file and printing its name and the number of members. Okay. These visitors are also context pairs, so you can do weird things like, okay, let's check that nobody in my library and my company has declared a class with a factory member function, a static member function, because we hate factories. Okay, you can statically assert that, and you will be much more happy without factories. Okay, back to our recipe for test function discovery. Number one, find any test case class. Okay, to find any test case class, you will have to get every class declared in your library, in your test executable, and check if that class is an actual test case class. Okay, so you visit all the entities reflected in the translation unit, you filter only, you get only the classes, and then check if that class inherits from our test case class. If that's the case, you run the test case discovery function. Okay? As you can see, all this branching and filtering and everything, it's fully context paired. Okay? There are no runtime decisions at all for test discovery. Everything is done at compile time. For test function discovery inside that test case class, you do more or less the same. You traverse all the member functions of this class and check if the method is named test underscore whatever. Okay? The only thing you have to have in mind is that sadly, C++ has no constexpr function parameters. So inside, even if the method metadata object is constexpr and instantiated at compile time, in the context of the body of the function, the parameter is not constexpr. So we cannot use it in compile time evaluated context, like this if constexpr, or an static assert, or whatever. So in tinyrefl, instances of entities are completely dummy, okay, because all the meta information is encoded into the type. But you instance this entity type just to have a nice object-oriented interface. So if you take the type that represents a fixed entity and reinstance it, in this case as a constexpr variable, you get exactly the same object with exactly the same properties. Okay, so this is a little trick to say, okay, this method, no, this is a constexpr object, I want my constexpr object again. Okay, so I can use it in the next if constexpr. If the test is an actual test method, we instance the test case and just call the method with the test case. Okay, and the implementation of each test method is as simple as checking if the prefix of the name of the method is test underscore. Okay. Where is my mind? The problem is tinyrefl, the parsing tool of tinyrefl works at the file level, at the header file level. So you don't have global project metadata information. So you cannot directly say, okay, let's traverse all the types declared or functions declared in my library or my executable. Okay, you have to have, in this case, one translation unit that includes all the headers, all the test headers in this case, with all its generated code metadata files, and then run test cases function. This is done through CMake because CMake can do almost whatever. And it internally, what it does is just run the tinyrefl tool again to actually register your files for reflection, and then generate a file like this, okay, with all your test headers, with all your test headers metadata files, and finally a simple main function calling the run all the test cases function. Okay, so okay, back to the patch function, because the patch is the real magic or interesting thing. Okay, what can we do to implement patch? It's simple. Just check the attributes of each test function. Okay, you can read these attributes through the reflection metadata. Check if there is an attribute named patch or tinyrefl patch in the tagged to this function, and then check the parameter of this patch attribute. Okay, so step by step, what this function is doing is, if this method has an attribute named tinyrefl patch, get the attribute, check or make sure that this attribute has only one argument, okay, and then read that argument as the identifier or global identifier of what is supposed to be a class method. Okay. Then we check through the reflection metadata API that it has a method called this way registered in the metadata. Okay, if this is not the case, this is an error, but this is a compile time error. You cannot patch with a wrong named function. It will not compile at all. Okay. If there is no patch attribute, you only call the test case as usual in the previous example, okay? But if you actually have a patch attribute, if you actually have one argument, this one argument is the full name of a method registered in the metadata, get the metadata of this method back, okay, through this identifier. And then just create a hook, like in the first example of elf-spy, create a hook of the right signature with the name of the method and the pointer to the method, okay, and then run the test case with the test case instance and the hook, okay. Future of the library, okay. When I submitted the talk to the CppCon proposals, I tried to have a parallel implementation of this unit test proof of concept with the Reflection Technical Specification, okay? But after like 6 months, I think, I found some real problems with this approach, okay? It's true that you no longer need an external parser and code generation tool because reflection is directly implemented by the language. It's true that you don't need any tricks like including some file in some order in order to get the reflection metadata. It's true, but you have no global reflection information, okay? You have no reflection of C++ attributes, and you have no global project metadata. This is the same problem with tinyrefl, so we can implement the same CMake trick, okay? But you have no global list of reflected entities, and you have no attributes. So what can we do? We can try and say, okay, instead of using unfiltered list of every entity declared by your library, we can try to say, okay, tests must be declared in the namespace testing, for example. So you can take the Reflection TS API, ask for the reflection information of the namespace : testing, and then try to get every member of the namespace, okay? But this idea didn't work either, because in the current specification of the Reflection TS, namespaces are not records. It means namespaces are not considered entities with members, with children, okay? They are plain entities. So you have no direct way to get the list of members of a namespace. You have a way to get the members of a class, for example, but you have no way to get the members of a namespace. So this either works. You have either parsing and reflection of C++ attributes. So using the cool attribute syntax for patching didn't work either. So you can try something like this using the return type of the test function, because test functions are 99% void returning functions. So you can use the return type to encode the patch, okay? And if you write in the upper line instead of the same line of the function, it looks mostly the same, okay? So my conclusion is that there is no way with the current Reflection TS to implement something like unit test, okay? We need more tools. We need global reflection information. We need namespace members reflection, and that's what we have currently, okay? You have to consider that the reflection specification target use case is about reflecting specific entities, like getting all the members of a function, of a class, getting the names of the parameters of a function, for example, or getting the string translation of an enumeration value, for example. Okay, so it's not designed to do full introspection of a program, of a library, no. It's designed to say, okay, here's my class, tell me what basis has, what members has, what constructors has. Okay, this is not designed for this, but I think we have time to change this, so maybe with time. Okay, so more ideas. This focused on the tinyrefl implementation. You don't have to use a class to write a test case. This comes from purely object-oriented programming languages like Java or Python or whatever, where you usually represent a test case as a class. Why? You can use a namespace or a module in Python, whatever. Okay? I would like to implement mocking of private functions. Okay? Currently, I cannot do this because tinyrefl doesn't know to reflect private members of a class. Actually, because I have found a way to get the pointer to a private function in a context that is not a friend of this class. So maybe there is a trick. If anyone has an idea, I'm open. I'm completely open for ideas. So also more ideas like multiple patches in the same function test, like Python unit test supports. And for example, implementing attributes as classes, like for example C# or Java, that attributes or decorators are actual instances of classes. So manipulating attributes and reading arguments of attributes is much more simple and natural than parsing a string. Okay? And that's all. Do you have any question?
It's not really a question, it's a stupid suggestion. When you say with the Reflection TS, we have no way of having a global view and finding all of the classes that might implement tests. I don't know about you, the way I do tests, that there is one class per executable. So actually, in that case, the class could be called test, and then we can use Reflection TS to find it, right? But obviously, this is limited. But do you think it would still be a possible approach to solve this problem?
Yeah, I think the approach is the Reflection TS is not finished, so we have time to actually add more stuff we are interested in. So instead of doing tricks, we can be talking about tricks like for 2 hours or whatever, but I would prefer to actually have a nice reflection API for C++.
Sure, I agree.
Any more questions?
Also a suggestion, you may want to take a look at Andrew Sutton's work, which can reflect namespace and also reflect attributes.
Really? Do you reflect attributes?
Yes. That was added on Monday. Yes.
Yeah. Look for it. This is the technical specification, like about 2 months ago or something like that. So.
And also, I agree with you that we should prefer the Python's unit test discovery mechanism because it's a standard mechanism. We don't want to invent a new one.
Yeah. No more questions? Okay. Thank you.